Let's wait for 2 minutes so that the rest of the people they can join. Okay, Ji, the next topic is can you hear me?
Yes, sir.
Okay, the next topic is collector feedback configuration circuit. Now in this one, what we have a circuit which okay, we have a circuit in which we have the collector resistance RC, then we have the transistor, and with the transistor we have the emitter resistance, and it is being connected to the ground, as well as if you see we have the base resistance, which is one end is connected to collector and the other end is connected to the base of the transistor. And with that we have the capacitor which is being connected, and that is connected to the input side, as well as we have the capacitor is connected, and from here we will be taking the output side. Okay, now as you know we are doing the DC analysis and we have the VCC which is being connected over here. As you know we are doing the DC analysis, so therefore the two capacitors which are C1 and C2 over here, they will be taken off, and once they will be taken off we will have the circuit that will be looking like this gone, and this is gone, so we are left with the circuit something like this, right? And with this one what we can see that there is a current which is flowing over here. Now that current which is flowing over here, we call it IC dash over here. It is going to split into two. One is the current which is flowing over here is the base current, and the other one is the collector current over here, IC, right? And similarly over here we have the drop which is VPE, and then there is a current which is flowing in the emitter leg is I, right? And there is also a drop between the collector and the emitter, which is normally being taken as VC. Are you with me?
Yes, sir.
Okay. From here, what we can see that we can have the input side as well as we can have the output side. The input side, if you see, it is basically the base emitter loop, but the base emitter loop is also having the base emitter loop is also having the so we have basically this whole side is going to be taken in the input side, right? And when we apply the KVL, the when we apply the KVL over here, so we can write the equation applying KVL to the input side. So we can write the equation over here. If you see, it will be equal to VCC is equal to the drop across the RC, and the current flowing in RC is IC dash. So this means we can have VCC is equal to IC dash RC plus we will have a drop across the base resistance RB. So the current flowing through the base is IB. So the drop over here will be IBRB, right? So plus IBRB, and then we will have a drop across the base emitter junction. The drop across the base emitter junction will be taken as VBE, right? So we can write plus VBE and plus the drop across the emitter resistance, so that will be IERE. Are you with me?
Yes, sir.
ठीक है जी? Question? Anybody having any question? Okay. With this, what we can see that as we have said that IC dash is equal to IB plus IC from the equation. Are you with me? But as IB is very small as compared to IC, so what we can say IC dash is approximately equal to IC, as well as we have IE is also approximately equal to IC because IB is a small value, right? So what we can say that this whole scenario will become VCC is equal to and we also know this thing, that IC is equal to beta times IB, right? So what we can write from this, that it will become beta times IB into RC plus IB into RB plus VBE and plus beta times IB into RE, because we are replacing IE and IC with IC, and IC is equal to beta times IB, right? So this means we can write VCC is equal to IB into beta times RC plus beta times RE plus RB plus VBE. Are you with me? आवाज आ रही है जी?
Yes, sir. Yes, sir. Are
Okay जी. So what we can write from here, that we can write IB is equal to VCC minus VBE divided by RB plus beta times RC plus RE. Are you with me? Is this thing fine? Any question?
Yes, sir.
ठीक है जी?
No, sir.
जी.
Yes, sir.
Is this thing fine?
Yes, sir.
Okay. Now if we say that, let's suppose this value which is in the numerator, VCC minus VBE, if we take this value VCC minus VBE as equal to V, or if I say it is equal to, let's suppose, V dash, and in the denominator if I say RC plus RE is equal to R dash, right? So this value IB can be modified as V dash divided by RB plus beta times R dash, right?
yes, sir.
And similarly, we know this thing from our knowledge that IC is equal to beta times IB, right? So putting the value of IB in this equation,
Yes, sir.
we will get IC is equal to beta times V dash divided by RB plus beta times R dash, right?
Yes,
Yes,
sir.
sir.
And if this value IB is at the Q point, this value IC will also be at the Q point, right? This means this value is on the load line, which is the DC load line. So what we can say, this IC value will become IC Q over, right? And if we say that in the denominator beta times R dash is very greater than RB, right? If beta times R dash is very greater than RB, so what we can say, ICQ is equal to beta times V dash divided by beta times R dash, right? So ICQ will become beta times V dash divided by beta times R dash. And as you can see, beta can be cancelled from beta in the numerator as well as in the denominator. So this means ICQ will be equal to V dash divided by R dash, right? Are you with me?
Yes, sir.
Now,
Yes, sir.
if you see, with the help of this equation, we see that the value of ICQ is actually independent of beta. So if the value of beta varies, there will be no change in the value of the Q point, or this means the point of operation of the transistor will not vary with the variation of beta, right? So due to that, if beta varies due to any of the circumstances, the value of the Q point will remain stable, right? Because the ICQ is independent of beta, right? And when it is independent of beta, this means the Q point is not going to vary. And when the Q point is not going to vary, this means this kind of a circuit is much more stable, or this has got the stability as compared to the other circuits, right? And this is basically a generalized equation. This can be replaced when we can see that what is the value of V dash and what is the value of R dash in all the circuits which we have seen up to, right? Because if you see, the values can actually vary from different circuits which we have seen up till now. We have seen different circuits. First one was the fixed bias, it was the emitter bias, then it was the voltage divider circuit, right? So and then this is the basically the fourth circuit which we are looking at, right, which is the collector feedback configuration circuit. Now the output side is actually the same as which we have seen up till now, and if you see in the circuit, the output side, is, if you see, if I draw for the output side, it will be something, this is the output side, right? And in the output side, if you see, we have, or here we have alhamdulillah, we have VCE, right? So again, if you write the KVL for the output side, the KVL for the output side will be KVL for the output side or output side, it will be we have VCC is equal to IC dash RC plus VCE plus IERE, right? As we know, IC dash is equal to IC and IE is also equal to IC. So again, the equation is transformed as VCC is equal to IC RC plus RE plus VCE, right? And this is the same equation which we are getting for the rest of the circuits, right? And the rest of the thing is the same which we have done up till now. So what you can do, you can add the, in the assignment you can add example 4.12 and you can add the example 4.14, 4.15, and that's it, right? So you can add in the assignment example 4.12, 4.13, 4.14, and 4.15, right? So again, this will be due in your before, like on Tuesday it will be due. ठीक है जी? So that's it from my side. So any question
कल
having?
होगा सबमिशन
जी,
सबमिशन डेट क्या होगा सर इसका सबमिशन डेट
ये next Tuesday. ठीक है जी?
यस सर थैंक यू
Okay जी. Any question?
नहीं है
Okay जी, ठीक है. Thank you. That's it for today.
Thank you, sir.
Thank you.
अच्छा